Download this code from codegive.com, link in the description below. Understanding movable objects, huge pages, and their impact on performance in C++. This tutorial will delve into the concepts of movable objects and huge pages, their benefits, and how they relate to memory management and performance optimization in C++ applications. We'll cover the theoretical foundations, practical implementation examples, and potential pitfalls to watch out for. Introduction. Modern C++ provides powerful tools for managing memory efficiently, directly influencing the performance and scalability of your applications. Two key concepts in this area are *movable objects, move semantics, a mechanism that allows the transfer of ownership of resources from one object to another without physically copying the data. This is particularly useful for large objects and can significantly reduce the overhead associated with copy operations. Huge pages, a memory management technique that uses larger virtual memory pages, typically 2 MB or 1 GB compared to the standard 4 KB, to reduce TLB, translation look-aside buffer, misses, improving memory access times. Using these techniques effectively can lead to substantial performance gains, particularly in memory-intensive applications. Let's explore each concept in detail and see how they can be used together. 2. Movable objects and move semantics. 2.1 The problem: copying is expensive. Traditional copy semantics in C++ create a completely new, independent copy of an object's data. While this ensures data integrity, it can be extremely costly for large objects, as it requires allocating new memory, copying all the existing data, and potentially performing deep copies of dynamically allocated resources. Consider a simple example. In this example, obj2 equals obj1 will trigger the copy assignment operator, resulting in a full copy of the data within the std vector. This is wasteful if obj1 is no longer needed after the assignment. 2.2 The solution: move semantics. Move semantics provide a way to transfer ownership of resources instead of copying them. When an object is moved, its resources, example dynamically allocated memory, are transferred to another object, and the original object is left in a valid but potentially empty state. This avoids unnecessary memory allocation and copying, leading to significant performance improvements. 2.3 Implementing move semantics. To enable move semantics for your classes, you need to define two special member functions. *move constructor *class name and other, no except. *move assignment operator *class name and operator equals class name and other, no except. Let's modify the large object class to include move semantics. Key points about move semantics no except specifies that the move constructor and move assignment operator will not throw exceptions. This is crucial for certain operations in the standard template library, STL, and ensures exception safety. If a move operation throws an exception, the STL may fall back to copying, defeating the purpose of move semantics. *std move * This function is essential for triggering move semantics. It casts an value, example obj1, to an value reference, example large object and, which signals to the compiler that a move operation is intended. Std move itself doesn't actually move anything, it just changes the type of the expression. *ownership transfer * The move constructor and move assignment operator transfer ownership of the underlying resources, in this case, the data vector, from the source object to the destination object. The source object is left in a valid but unspecified state, often an empty state. It must remain in a destructible state, though. Asterisk self-assignment check asterisk in the move assignment operator, it's important to check for self-assignment, example obj equals std move, obj. If the object is assigned to itself, simply return asterisk this without doing anything. This prevents the object from destroying its own resources. 2.4 When are move operations used? Move operations are implicitly used in several situations. Asterisk returning objects by value from functions asterisk. Asterisk inserting elements into std vector, and other STL containers, when the element is being moved. This is especially important when resizing vectors, as the existing elements might need to be moved to a new memory location. Asterisk using std move to explicitly request a move operation. 2.5 Advantages of move semantics. Asterisk reduced memory allocation. Asterisk avoids unnecessary allocation and delocation of memory, leading to faster execution. Asterisk improved performance. Asterisk reduces the time spent copying data, especially for large objects. Asterisk exception safety. Asterisk when combined with no except, move semantics contribute to more robust and reliable code. Asterisk enables move-only types. Asterisk some types, like std unique underscore ptr, are designed to be move-only, not copyable. Move semantics are essential for working with these types. 3. Huge pages. 3.1 The problem, TLB misses. Modern operating systems use virtual memory to provide each process with its own isolated address space. The virtual addresses used by a program are translated to physical addresses by the Memory Management Unit, MMU. The TLB, translation look-aside buffer, is a hardware cache that stores recent virtual to physical address translations. When a program accesses memory, the MMU first checks the TLB. If the translation is found in the TLB, a TLB hit, the physical address is quickly obtained. However, if the translation is not found in the TLB, a TLB miss, the MMU needs to perform a slower page table walk to find the physical address. This page table walk involves traversing a hierarchical data structure in memory, which is significantly slower than a TLB lookup. For applications that access large amounts of memory, TLB misses can become a significant performance bottleneck. The default page size, usually 4 KB, means that a large number of pages need to be tracked, increasing the likelihood of TLB misses. 3.2 The solution, huge pages. Huge pages address the TLB miss problem by using larger memory pages. Instead of 4 KB pages, huge pages are typically 2 MB or 1 GB in size, depending on the operating system and hardware. This means that fewer pages are needed to map the same amount of virtual memory, reducing the pressure on the TLB and decreasing the frequency of TLB misses. 3.3 Enabling huge pages. Enabling huge pages typically involves a few steps. 1. Operating system configuration asterisk. Asterisk Linux asterisk. Asterisk allocate huge pages in the kernel. Asterisk create a mount point for hugedelbs, huge page file system. Asterisk optionally, configure the system to automatically allocate huge pages on boot by editing /etc/sysctl.conf and adding the line vm.nr_hugepages equals 1024. Asterisk Windows asterisk. Asterisk grant the lock pages in memory privilege to the user running the application. This can be done through the group policy editor, bedite.msc. Navigate to Computer Configuration - Windows Settings - Security Settings - Local Policies - User Rights Assignment and add the user to the lock pages in memory policy. Asterisk, Windows does not typically use a file system-based allocation method like Linux's hugedelbs. 2. Code modification, Allocation with huge pages. There are several ways to allocate memory using huge pages in C++. Asterisk using POSIX API, Linux. Explanation asterisk. 1 open, /mnt/hugepages/my_hugepage, asterisk opens, or creates, a file within the hugedelbs mount point. This file will back the huge page allocation. 2 truncate, fd, huge_page_size, asterisk resizes the file to the desired huge page size. This is essential for allocating the memory. 3 map, null, huge_page_size, asterisk maps the file into the process's address space. The map_shared flag is used because huge pages are generally shared between processes. The prot_read prot_write flags allow both reading and writing to the mapped memory. Null indicates the kernel chooses where to map the file in the address space. 4 close, fd, asterisk the file descriptor is closed after mapping the memory. The mapping persists even after the file descriptor is closed. 5 munmap, address, huge_page_size, asterisk unmaps the memory when it's no longer needed. Asterisk using boost.interprocess, cross-platform. Boost.interprocess provides a more portable way to allocate shared memory, including support for huge pages. Explanation asterisk. 1 BIP managed_shared_memory asterisk creates or opens a shared memory segment. The create_only flag indicates that the segment should be created if it doesn't already exist. The true argument passed after the size requests the segment to be backed by huge pages, if available. 2 BIP allocator asterisk creates an allocator that allocates memory within the shared memory segment. 3 segment.construct int, myDataArray, 1024, allocator, asterisk constructs an array of 1024 integers within the shared memory segment, using the provided allocator. 4 segment.destroy_int, myDataArray, asterisk destroys the array when it's no longer needed. This is optional, as the shared memory segment will be destroyed when the program exits. 5 BIP shared_memory_object remove, my huge page segment, asterisk removes the shared memory segment. This is essential for cleanup. 3.4 When to use huge pages. Asterisk large memory footprint asterisk applications that use a significant amount of memory, example databases, scientific simulations, machine learning, are the primary beneficiaries of huge pages. Asterisk random memory access asterisk applications with a high degree of random memory access, as opposed to sequential access, are more likely to suffer from TLB misses. Asterisk virtualization asterisk huge pages can improve the performance of virtual machines by reducing the overhead associated with memory virtualization. 3.5 Advantages of huge pages. Asterisk reduced TLB misses asterisk decreases the frequency of TLB misses, leading to faster memory access times. Asterisk improved performance asterisk can result in significant performance gains for memory-intensive applications. Asterisk reduced overhead asterisk reduces the overhead associated with managing memory pages. 3.6 Disadvantages of huge pages. Asterisk memory fragmentation asterisk huge pages can lead to memory fragmentation if they are not used efficiently. Because they are large, it can be difficult to find contiguous free blocks of memory large enough to satisfy huge page allocation requests. Asterisk configuration overhead asterisk requires operating system configuration and code modifications. Asterisk limited availability asterisk the availability of huge pages can be limited by system resources and configuration. You need to pre-allocate huge pages in the kernel, and if those are used by other processes, your application may not be able to allocate them. Asterisk increased memory consumption asterisk even if you don't fully use a huge page, it's allocated. This can lead to wasted memory. 4. Combining movable objects and huge pages. Movable objects and huge pages are complementary techniques that can be used together to optimize memory management and performance. Asterisk movable objects avoid copying into huge pages asterisk when data is allocated in huge pages, copying large objects into or out of these pages can be expensive. Move semantics allow you to transfer ownership of the data without performing a physical copy. This is especially useful when constructing objects within the huge page region or when returning them from functions that operate on huge page data. Asterisk efficient resizing asterisk when using STL containers like std vector with elements allocated in huge pages, move semantics are crucial for efficient resizing. As the vector grows, existing elements may need to be moved to a new memory location. Move semantics ensure that this operation is performed efficiently, avoiding unnecessary copying. Example, vector of movable objects in huge pages. This example demonstrates how to create a std vector of large object, with move semantics, within a huge page region using the POSIX API and map. Explanation asterisk. 1 huge page allocation asterisk the first part of the code allocates a huge page using the map approach described earlier. 2 placement new asterisk std vector large object asterisk vec equals new, address, std vector large object, uses placement new to construct the std vector directly at the beginning of the huge page region. Placement new allows you to construct an object at a specific memory address. This is crucial because the regular new operator would allocate memory from the standard heap, not the huge page region. 3 Emplace _back, and push _back, std move, asterisk the emplace _back, method constructs a large object directly within the vector, avoiding any unnecessary copies. Push _back, std move, obj, uses move semantics to efficiently transfer the resources of obj into the vector without copying. 4 Explicit destructor call asterisk since we used placement new, we must explicitly call the destructor of the vector using vec-vector, before unmapping the memory. If you don't call the destructor, the objects within the vector won't be properly destroyed, which can lead to memory leaks or other issues. Potential pitfalls and considerations. Asterisk alignment asterisk when using huge pages, ensure that your data structures are properly aligned to the huge page size. Misalignment can lead to performance penalties. The aligness specifier in C++11 and later can be used to enforce alignment requirements. Asterisk fragmentation asterisk be mindful of memory fragmentation when using huge pages. Avoid allocating and deallocating huge pages frequently. Consider using a custom memory allocator that is optimized for huge pages. Debugging applications that use huge pages can be more challenging. Use memory debugging tools to identify potential memory leaks or corruption issues. Portability huge page support can vary across operating systems. Use conditional compilation or cross-platform libraries like boost.interprocess to ensure portability. Error handling always check the return values of system calls related to huge page allocation and mapping. Proper error handling is essential for robust code. Performance testing thoroughly test your application with and without huge pages to determine whether they provide a performance benefit in your specific use case. Not every application will benefit from huge pages. It depends on the memory access patterns. 6. Conclusion. Movable objects and huge pages are powerful techniques for optimizing memory management and improving the performance of C++ applications. By using move semantics, you can avoid unnecessary copying of large objects, reducing memory allocation overhead and improving execution speed. Huge pages reduce TLB misses, leading to faster memory access times for applications with large memory footprints. However, it's important to understand the potential pitfalls and considerations associated with these techniques. Proper planning, careful implementation, and thorough testing are essential for achieving the desired performance gains. By combining these techniques effectively, you can create more efficient and scalable C++ applications that can handle large datasets and complex computations with ease. Remember that the benefits of these techniques are highly application-specific, so always benchmark your code to ensure that you're actually achieving a performance improvement.